Right, gents. Last week, those of you that were here or watched the video, the first part of the session was about induction motors, and that's around part of what you're being asked to look at in the assignment. So, and then some calculation stuff towards the end. I'm going to do something similar this week. So the first assignment is issued today. I haven't got printed versions of that for you. It's on the website. If any of you are not unable to get to Learn UCS at the moment, and I can't remember whether you've all tried it, but if not, well, I can email it out. We can sort it out. So in a similar fashion today, I'm going to go through a little bit around the speed control of induction motors using variable speed drives or inverters. Again, what I'm trying to do is model the level to which you'll study the other type of motor the assignment's based on, and do a comparison between the two. So we'll have a look at the assignment later, and I'll give you a few tips as to what the types of things I'm looking for you to do. So up front this week, we're going to look at the speed control of induction motors, then a brief intro to the assignment, and then some more stuff on calculations with power circuits towards the end of the session. And again, there's a tutorial worksheet for calculations. Okay, so speed control of induction motors. Popular way to achieve that is using ASDs, adjustable speed drives, commonly known as inverters. Devices available for around 20 years, suit a wide range of applications from single motor pumps, fans and compressors to sophisticated multi-drive machines. Okay, the industry I come out of, quite common to use to control conveyors, because if you've got bottles standing up on a conveyor, if you try and just direct online start a motor, they all fall over. But if you ramp them up and ramp them down, even a little bit, that tends to stop and waver and so much, and they don't fall over. They operate by changing the frequency of the AC voltage applied to the motor. So, as we talked about in last week's session, the synchronous speed of the motor is all related to the frequency of the sine wave in the first place. Well, our AC mains in this country is fixed at 50 Hertz and ain't going to change. So the way the inverter works is to use electronics to produce a sine wave that we can vary the frequency of. It's fairly expensive to provide a high degree of control, and in many cases, it provides a high degree of control. In many cases, reduces the energy used, which offsets some of the extra cost. So it's the installation costs that are the issue, and again, we'll come back to that along with some other disadvantages later. But it does allow the precise control of a standard induction motor. I mean, going back to my fibrinol days and the extrusion of plastic, the old extruders had what's called pillar motors on them. They were made by some company in Germany. Now this elaborate affair with double set of commutator brushes. I still don't really know how those motors gave a continuously variable speed, but the two sets of brushes turned independently of each other, and the only thing I could think was that varied the number of poles or in some way, or varied the number of coils that you had, but there was a little motor operated these brush rings. Well, they were a nightmare for getting loads of carbon. You had slip rings one end, you had brushes the other end. The things would get full of carbon, track across to get big bangs and stuff. The maintenance on them was massive. But with the advent of reliable inverters, we could just retrofit an induction motor with an inverter, and it got a good range of speed control, infinitely variable between 2 points, and that's what you're looking for. There are issues around it, which we'll touch on a bit later in today, but they are pretty good and pretty reliable. Because you're using a bog standard induction motor, there ain't a lot going to go wrong with that too many times a decade. Alright? So, these adjustable speed drives, what they do is they take the AC sine wave, and the simplest way to describe what an inverter does is it takes the AC mains, either 400 three-phase or single phase, and that's another thing. You can run a three-phase motor on a 240 volt outlet with an inverter, because that inverter is creating the three-phase rotational magnetic field that you need. You have to be a bit careful about the selection of the motor, and I believe if from memory you have to connect it in delta rather than in star, so you've got to get a dual voltage motor, because that's going to be three-phase 240 volts. Yeah, but it can be done, and that's handy for small conveyors. What it does, the simplest I always describe it is it takes the AC mains, rectifies it to DC, so you've got some big capacitance inside inverters for smoothing and such like, rectifies it to DC, and then uses a microprocessor to recreate a sine wave, and because you're using that microprocessor to recreate the sine wave, you can vary the frequency of it. Okay, so there's a converter, inverter and regulator. All that is to recreate the sine wave, but in a way that we can vary the frequency of that sine wave. So ignoring slip, the speed of induction motor can be calculated from that formula. The 60 in there is because we're going to go from RPM, the number of turns a second in RPM, to frequency in hertz, which is cycles per second. Okay, but that will get, so if we have a 4-pole motor operating on 50 hertz, the synchronous speed would be 1500 RPM. If that was on 40 hertz, it'd be 1200 RPM. So that's sort of showing just by varying the frequency, we can vary the speed of the motor, because that rotating magnetic field is going around once for every cycle, 360-degree cycle of the mains. Inverters actually, they control both the frequency and the voltage simultaneously to maintain constant volts frequency ratio, which keeps the current flow similar to full speed conditions. So it isn't just about controlling the frequency, also controls the voltage as well. This allows the motor to draw full current at any speed and therefore produce full torque as the motor speed changes. What happens to the power when the lower speed and torque using frequency? You can find out that from that formula. Hence, if we reduce the speed, we reduce the power drawn and reduce the energy use, which must reduce the cost of running. Okay, so if the RPM is reduced, that top line is reduced, therefore that number must become smaller, you're using less power. Some specifically designed motors can operate at higher than normal speeds, i.e. at frequencies above 60 hertz, but there are two primary concerns with that. One was the motor or loaded drives designed to operate at the higher speed, so unless the limits are set on frequency on the inverter, someone could whack it up to, let's say, 100 or 120 hertz. But was connected to it, designed to work mechanically at that speed? Is the motor rated mechanically to turn at twice its normal rated speed? And is the equipment connected to it meant to work at that speed as well? Secondly, inverters are not capable of increasing voltage, so at frequencies above the design of that motor, they can't put more voltage in. So that means the torque will start to reduce because the current's going to go down. So although you can do it, there are implications to running beyond the design speed of the motor. Some point that will lead to the motor speed decreasing despite you asking it to increase the frequency, because less current, eventually you get to that point where a law of diminishing returns cuts in. Advantages and disadvantages. We look at these individually, but inverters do have a number of advantages and disadvantages. Their advantages are in energy saving, improved control of the process, reduced voltage starting, lower maintenance. They're easily bypassed. So if you had an emergency situation, that pump must start up and go flat out, or you want to take the inverter out, you can bypass them fairly easily. It's not true of some other systems. And there are systems where they can control multiple motors using one controller. Disadvantages are the initial cost, heating of the motor at low speeds, maintenance of the inverter itself, output harmonics, and the induced harmonics they can put on power lines. This can be quite a big issue. So energy savings can be used to save a significant amount of energy compared to traditional methods of control. Among the most efficient types of speed control, when they're used on axial variable torque loads like centrifugal fans, pumps, compressors. As the motor reduces the operating speed of the fan, pump or compressor, the horsepower required to operate is greatly reduced. So if you need less horsepower, you're going to use less power in the first place, you're going to save energy. This is a major advantage of ASD, and one of the primary reasons why they've become so popular is to save money. Variable torque loads require much lower torque at low speeds than at high speeds. Torque required varies as the square of the speed, and the power required varies as the cube of the speed. So when the speed of a variable torque load is reduced to 50%, the torque required to drive a load is reduced to 25%. Horsepower is reduced to 12.5% of the amount required to drive it at full load speed. Variable torque loads include axial pumps, fans, blowers, mixers and agitators. So there's a huge savings to be made there if you get it right. Okay, not suitable for every type of load, but general loads they are particularly good for. Constant torque loads require the same amount of torque at low speeds as at high speeds. So torque remains constant through the speed range, and the power increases and decreases in direct proportion to change in speed. If the speed drops to 50%, then the power required to drive the operation will drop to 50% while the torque remains constant. Constant torque loads include most conveyors, positive displacement and reciprocating pumps, and compressors. Advantages: reduced voltage starting. An ASD acts like a reduced voltage starter to limit the amount of inrush current when the motor starts. So we all know what the ammeter does on an induction motor when you push the start button and you get that big starting current flow. The ASD acts to reduce that, so it can limit this inrush current to a maximum of 150% of full load current. And any one of you that set one of these up know there's a whole list of parameters you can adjust on these things. They don't just give you control over the frequency and speed of the motor. They can do all manner of other adjustments that I've never even needed to understand what they do, but they obviously do something because they want to put them on there otherwise. but various braking parameters and different things that you can do. So another advantage is you get improved process control. So it's like a solid state electronic device lends itself well to automated process control. Can take signals from start, stop and speed control to either hold a motor at a particular speed, or maybe you want to vary the speed of a pump so that you can keep a variable delivery flow rate the same. So where the demand changes, but you want the flow rate to be 10 litres per minute, you can have a sensor that will sense that and use the inverter to vary the speed of the motor and at least attempt to maintain that constant flow rate. Other types of variable speed control can be very limited as to their interface to the process control system or have no capability whatsoever. So these are pretty good for that, inverters. Bypass capability. But it's quite easy to be able to parallel up a direct online starter with a system, because what you put into the inverter is exactly what you would deliver to the starter. You could parallel that up. So if you need to take the inverter out for any reason, you've got a bypass facility that you can just start the pump up direct online. So that's the idea. It makes that easier for you to be able to take the inverter out for maintenance. And it's not true of all the different types of speed control system. Some ISDs can control multiple motors from the same drive, which can be an advantage over other types of variable speed control drives. The advantage of this is a smaller physical size of the control being used, as well as a reduced initial cost of the ISD system. If you can buy, maybe they cost a bit more than a one that will control one motor, but not as much as two single motor controls. I don't know, I'm not an expert in that field. ISD disadvantages. Not the best choice for all variable speed applications. Some of the drawbacks to using an ISD, which are generally the advantages to using other types of speed controls, are as follows. First of all, the initial cost. Generally greater than other types of variable speed controls. Common obstacle for a process plant to install the ISD. Payback from energy savings has been the traditional way to justify using them, but the energy payback is low for applications where average speed requirement is near the motor's rate speed level. If you're not slowing it down very much, you aren't going to be using that much less power, and therefore it's going to be using a similar amount of energy to what it would be if you were running it direct online. So your payback there is not going to be so quick. As a general rule, a payback of 2 to 3 years typically will justify using an ISD. Maintenance. The motor is easy to maintain, simple induction motor, but the ISD itself, like many other solid state electronic products, require special troubleshooting knowledge for operations and maintenance personnel. Maintenance personnel can obviously look at a mechanical type of device and see if there's something wrong with it, but that's not so easy to diagnose the complex electronics within an inverter. Having said that, they don't go wrong very often in my experience. So, you know, there's to's and froms. You ain't, as a user, as an end user of a three-phase inverter, you probably aren't going to have the lab equipment and the test equipment to go down to board level and find out what's wrong with that if it breaks down. You're probably going to send that one back and get a replacement, or you're going to get somebody else to fix it. So there's that disadvantages that's not usually end user serviceable. One of the biggest disadvantages is the disadvantage of the motor overheating at low speed operation. Because people can run them really slow, I'll tend to think that's great and that's okay to do that. But most induction motors are cooled by a fan on the back of them. So if the motor's going slower, it's going to get less throughput of air and it's not going to cool properly. So there are limits as to how slow you can run this thing, particularly if it's running constantly at that low speed. Right. No matter what speed the motor runs, the current drawn to the motor will be the same with a constant torque load. At low speeds, the cooling fan produces less air and therefore it's going to overheat. So what you need to do is be a bit careful about what class of motor and what class of insulation your motor's got to prevent it from burning out if you're going to be running at low speeds for a significant length of time, is what most of that slide is saying. Yeah, and I know for a fact that they get the one conveyor motors that we had that run right slow, even though they're gearboxed down slow, so they're still running relatively fast, but on low frequencies, 10, 12 hertz, they get hot quick and they do burn out more than ones that are running direct online. Disadvantage, output harmonic distortion. The output electrical waveform generated by the ISD is not a perfect or a pure sine wave. It's one created by pulsing the output, as created from a square wave, effectively, where they control the width of the pulse to recreate close to a sine wave, and there's filtration used. So it includes what's called harmonic distortion that goes to the motor. The harmonics, they're multiples of the fundamental frequency, so if your output frequency is 40 hertz, the second harmonic of that would be 80 hertz, the third would be 120 hertz, and so on. So this recreated sine wave is going to be one made up of a number of controlled harmonics. That'll create heat in the motor. As a rule of thumb, ISDs will create between 5 to 8% extra heating in a motor as compared to the same motor running on a sinusoidal waveform from the mains power. One way to overcome that again is to look at the class of insulation you're using with your motor and to uprate your motor a bit to compensate for that. Induced power line waveform distortion. The ISD in a solid state electronic load will cause waveform distortion to be induced on the electrical input supply, the supply coming in. Now, if that's not dealt with, what it's effectively doing is going to distort the national grid to a certain extent. You're distorting the incoming waveform, which is not a good idea. So the waveform is distortions created by the ISD consists of both harmonic distortion and what's called line notching. A result of the non-sinusoidal waveform of the drive, which pulls the current off to the power line in non-sinusoidal pulses. This can severely distort the electrical power supply within the facility, so within this college or within your manufacturing facility, and if not properly protected, can hinder the operation of other devices. So other sensitive electronic devices ain't necessarily going to like that. Operations using ISD in the vicinity of sensitive electronic equipment should consider including an isolation transformer or line reactor on the input that drive to protect other equipment. So you put some kind of protection in. The inverters are used if you have solar panels on your house. What you've got there, you have an inverter, but you don't need the rectifier bit because you're getting DC anyway. And then what they do is they take that DC and they invert and create the sine wave so you can put that electricity back on the grid effectively with in-feed tariff. So those inverters are have to be very specific about the filtration of our output so that they don't output non-sinusoidal waveforms on our national grid. So they're a specialist that's designed for that application as opposed to the motor application that we're talking about. That concludes my little bit of a introduction to what ISDs do in terms of controlling the speed of a three-phase induction motor. All right. Have any of you got any questions around that?